The chemical compound that I'll be explaining today is hydrogen selenide. I will begin by explaining the Lewis dot structure. So here we have the Lewis dot structure. It's not linear as we would assume, since we do have two lone pairs as are seen right here. This is the reason why it's not a linear structure, and it's very similar to water because of the same reason that water has lone pairs. Also, we have a total of 8 electrons. Here we have the Vesper diagram, which shows more of the bend structure than the Lewis dot structure. So this is going to give us a better reference on how the angle would appear, and when we go to our contour diagram, which is a little further in this presentation, we will see that it's more realistic of how it actually looks than the Lewis dot structure. The Vesper diagram also shows us that we do have two lone pairs, and then we have two bonding pairs, which is the hydrogen. So total we have 8 electrons, and this also shows us the hybridization orbital, which is sp3, mostly because it is bent. Just as you can tell, this is bent right here, because also the lone pairs are pushing it to become bent, but I'll be explaining that more forward. And it's sp3 because it's a total of 4 orbitals, so this gives us 1, 2, 3, and then 4. Now we have the electron box diagram for selenium. We have 4s and 4p. We have 4p because if you were to look at the periodic table, we will see that selenium falls into the 4p, and we know that selenium has a total of 6 electrons due to the periodic table, so then that explains why our 4p is filled up. And since it is filled up, there's no need for no electrons to be promoted, which is why we do not have an excited state, and we would just go straight to hybridization. Also, the electron diagram also represents the two lone pairs of selenium, which is these two right here. So when we're going to hybridization, we'll know what is going to bond. So since it did not have an exciting state, and now we could go straight to hybridization, it's very similar to the electron diagram in the beginning. So as you can tell, this portion stayed completely the same, but since we're hybridizing, then this part is going to be different. So since we do have two lone pairs, that's going to show us that we're going to have 2 sigma bonds, which are right here. So our hybridization orbital is sp3, which we have labeled here. Oh, and this is considered the bonding state of selenium. So when it's being hybridized, it's pretty much we're making new hybrid orbitals. So we have a total of 2 lone pairs, which are represented in the sp3 orbital right here. And then we have 2 lone pairs right here, which were the 2 lone pairs that were in the 4p. So we also want to make these into bonding pairs, so then that's when we use that 2 hydrogens that were attached to selenium, and we bind those 2, which give us the 2 sigma bonds. So we're binding the hydrogen with one of the sp3, and then the other one the same. So then that would give us a total of 2 lone pairs and 2 bonding pairs for this compound. Next, we have the contour diagram. So by using the information in hybridization, we're able to draw it. We have our lone pairs here, and then we have our bonding pairs down below. As you can tell, our sp3s are binding with the hydrogen, which is the 1s. The bonding pairs are also our sigma bonds, which is only 2, since we only have 2 bonding pairs. lone pair and bonding pair repulsion is much greater than bonding pair repulsion, and because of this reason, the lonely pairs that we have up here above are pushing these bonding pairs together, which give us a bent angle, which is less than 109.5. But since it's very similar to water, that angle could also be roughly 105. To end this presentation, these are our 3D diagrams of hydrogen selenide. This was using a molecular kit. So this represents one lone pair, and this represents my other lone pair. This is one bonding pair and another bonding pair. Also using a 3D application, we did it over here as well, hydrogen selenide. So we have our two bonding pairs as well, the hydrogen with the selenium. And then we have our two lone pairs out here.